We have been spending a lot of time on the foundational work of Git Day, the deep, solitary process of writing history.
hmm
We're talking about staging, committing locally, creating branches, merging.
Yeah, all those crucial steps happen entirely on your machine, contained right within your local repository.
It's like writing a brilliant private diary. I mean, the insights are there, the history is perfectly ordered, but only you can read it.
Right. And as important as that local integrity is, code development is rarely a solitary endeavor.
Exactly. Eventually, you have to publish the book.
Right.
You have to share your work, collaborate with a team, and perhaps most importantly, move that precious history somewhere safe.
That vital off-site backup.
For sure.
And that shift from isolated work to integrated teamwork is where we land today. We're talking about the critical bridge that moves those local committed changes, those packets of work, to the shared central repository.
Which is, of course, the command git push.
Git push.
It's the mechanism that broadcasts your finished work to the world, or at least to your team. For anyone studying, collaborative workflows or targeting professional certification like the GitLab Certified Git Associate exam, mastering this command isn't optional.
No, it is the absolute gateway to being a contributor. So our mission today is to take the seemingly simple two-word command and really unpack its mechanics.
Understand the critical tracking relationships it creates
And most importantly, internalize the safety protocols that prevent total collaboration chaos.
yeah.
We're moving from local historian to professional broadcaster.
Okay, let's unpack this by starting at the destination. We keep referring to the remote. If Git is already on my machine, what exactly is a remote repository? Why do I need one?
The remote is, well, it's exactly what it sounds like. It's a copy of the repository that resides externally.
So not on my laptop.
Not on your laptop. It's the source of truth. Sitting on a shared server, maybe a cloud platform like GitLab or GitHub or a network drive that the whole team can get to.
I like to think of it less as just a repository and more as the official shared contract of the project.
That's a great analogy. It's the single place everyone agrees is correct.
Right.
And because Git is so collaborative, it uses a key convention to standardize that shared contract. Git universally names the default primary remote repository origin.
Okay, so why origin? Why not something like main server or shared code?
Well, because when you first clone our repository, that location, the place you pulled the code from, is the project's point of origin.
Ah,
So Git tags that remote source with this default name. It just gives us a universal vocabulary. When any developer runs a command like git push origin, we all know exactly where that code is heading.
So when I interact with origin, what am I essentially doing for the team? What is its core function?
It serves two equally crucial dual purposes. First, the most obvious one is collaboration.
The central hub.
It's the central exchange hub where multiple team members can access, contribute, and integrate their work into the same growing history.
And the second one?
The second one, and this is the one people often overlook until it's too late, is backup. That committed code is redundant.
So if my hard drive dies,
If your local machine suffers a catastrophic failure, your work is still safely recorded on origin.
that puts the push command into perspective. We're not just sending data, we're fulfilling our team obligation and, securing our own work.
Exactly. So the essential wisdom here is when you push, you are almost always directing those committed changes to the standard remote origin.
So we've established the where, the shared source of truth. Now let's dive into the how, the command structure itself. The basic command is just git push. But when you're dealing with origin, you usually need more specifics, right?
You do. When you run a push, Git needs to know two things: which remote you're talking to and which local branch you want to replicate on that remote.
So the full structure is something like git push, remote name, local branch name.
Precisely.
So if I'm working on a brand new feature to make the app green, let's call it branch feature emerald mode, and I want to share it for the first time, I would run git push origin feature emerald mode.
That command tells Git exactly what history to move and where to put it. However, and this is a big however,
Oh, yeah.
if that branch feature emerald mode has never existed on the remote before, that command alone will fail.
Okay, this is where it gets interesting and where a lot of newcomers hit their first real snag.
For sure.
Git knows the branch exists locally, but it doesn't know how to create that persistent connection on the remote.
Correct. The very first time you push a new branch, you have to establish a critical link, what Git calls the tracking relationship.
We do that by setting an upstream branch. What does upstream even mean here?
Think of your local branch as a canoe and the remote branch as a dock. Right now, your canoe is just floating around. The U flag is the rope that permanently ties your local canoe to that specific remote dock.
Okay, I like that.
So upstream is just the convention Git uses to denote the source it should pull from or the destination it should push to for this specific local branch.
So I have to manually tell Git, hey, future me is going to want to constantly interact with this specific branch on origin, so please remember this connection.
Exactly that. You are configuring your local branch to track the remote branch. The long explicit command for this setup is git push set upstream origin feature emerald mode.
And since we as developers value efficiency,
We use the universally recognized shorthand. That entire command is usually replaced by the much shorter and easier to type git push u origin feature emerald mode.
that tiny little U.
That tiny u is the crucial one-time setup fee that saves you, potentially hundreds of keystrokes later.
And that's the real payoff.
Yeah.
Once I have used the edu flag successfully for the first time, Git remembers that tracking relationship.
Right.
So the next time I make commits on feature emerald mode, I can just type the glorious 3-word command, git push.
That's it. No need to specify the remote or the branch again. Git consults the tracking relationship you establish and just defaults to pushing your changes to the associated upstream branch on origin.
It only works because you took the time to set up that connection first.
Precisely.
Okay, that clarifies the how. We can send our code. But now let's talk safety. This is where collaboration can transform from a smooth process into a daily peril. What happens the second my colleague pushes their code while I'm committing?
Yeah.
What prevents me from just overwriting their work the moment I run git push?
This is the genius of distributed version control, and specifically the primary safety check the remote repository performs. It enforces what we call the superset rule.
Sounds a little academic. Can you translate the superset rule for us?
It's quite simple in practice. Your local branch history must be a superset of the remote history before your push is accepted.
A superset, meaning it has to contain everything the remote has, plus my new stuff.
Exactly. Think of your commit history as a sequence of building blocks, numbered 1 through 10. The remote branch has blocks 1 through 7. To push, your local branch must contain every single block the remote has 1 through 7, plus your new blocks 8, 9, and 10.
So if the remote is at block 7, and I push my block 8, 9, and 10, I'm good because my history seamlessly extends theirs.
Exactly. It's a continuous, uninterrupted chain. Git loves that. But here's the daily scenario.
Okay.
You start working when the remote is at block 7. While you are committing your work, let's say blocks 8 and 9, your coworker pushes their commits, we'll call them blocks A and B, and the remote history advances. The remote is now at block B.
Wait, blocks A and B are completely different from my blocks 8 and 9.
Right. If you try to push your history now, the remote looks at your local branch and says, hold on, you are missing blocks A and B. If I accept your push, I have to delete A and D to replace them with 8 and 9.
Which breaks the history chain.
It breaks the chain. And this is where the push rejection happens. Git throws up a roadblock because your local branch is no longer a superset of the remote. It's an incompatible version of history.
So you get that error message.
Correct. You get a clear error message that says something like, updates were rejected because the remote contains work that you do not have locally. It's a polite but very firm instruction.
This mechanism is really Git's way of prioritizing history integrity. It forces the responsibility of conflict resolution onto the individual developer before they can broadcast potential chaos to the team.
That's the core safety protocol. If you get that rejection, you can't just retry the push. You have to follow the required, non-negotiable standard workflow.
Which starts with git pull.
First, you must execute git pull to fetch those new commits, blocks A and B, and integrate them into your local history.
That integration is usually a merge. So now you have a complete set of blocks, 1 through 7, plus A and B, plus your 8 and 9, and a new merge commit.
Now your local history contains everything. It is the true superset.
And only then, when my history is fully reconciled and linear with the remote.
Then you can safely run git push. The remote sees your branch as a valid continuation of its own history, accepts the changes, and broadcasts your new combined history to everyone else.
So the mantra is pull, work, commit, pull and merge, then push.
Always.
That's a fantastic walkthrough of the mechanism designed to keep us safe. But now we have to talk about the command that completely subverts that safety protocol. Let's venture into the exam danger zone.
Ah, yes.
Force pushing.
This is the command that makes seasoned developers sweat a little bit. It is the ultimate expression of confidence or, more often overconfidence.
And the command is git push force, or the short form.
The infamous git push F.
If the superset rule is the safety guardrail, what does the force flag do?
It tells Git to dismantle the guardrail. Just ignore the superset rule entirely. You are telling the remote server, I don't care what history you have, I don't care if I'm missing commits, wipe out whatever is there and replace it with my local branch history.
That sounds absolutely terrifying in a collaborative environment. Let's go back to our scenario. My colleague pushed block A and B. I got rejected. But instead of pulling and merging, I get impatient and run git push force. What happens?
In that moment, blocks A and B are effectively deleted from the remote's shared history.
Gone.
They are overwritten and replaced by your blocks 8 and 9, even though your commits were based on older, outdated remote history. Your coworker and everyone else on the team will eventually pull down your forced history, and their local repositories will suddenly indicate the blocks A and B never even happened.
That is the very definition of destroying collaboration. The time lost trying to reconstruct that lost history is immense.
Which is why this is specifically flagged as a high-risk operation in certifications and in, well, every professional development team. It should never, under any circumstances, be executed on a shared branch, especially main or develop.
Any branch where other developers rely on history integrity.
The risk is just too high.
Okay, so if it is so dangerous, why does the command even exist? There must be some narrow sanctioned use case.
There is. Force pushing is used almost exclusively for advanced cleanup operations, specifically when you are using commands like git rebase to rewrite and simplify your commit history.
Ah, right, because rebasing changes the commit IDs, which effectively rewrites local history.
Exactly. You might rebase a feature branch to clean up dozens of small work-in-progress commits into one perfect, clean commit. But since those new clean commits have new IDs, they are no longer a superset of the messy commits you previously pushed.
So you have to force push.
You have to force push to replace the messy remote history with your clean rebased history.
And the critical caveat there is that you should only do that rebase and force push on a branch that only you have been working on.
And that no one else has pulled yet. If it's your history, you can clean it up. If it's shared history, hands off.
It's the difference between cleaning your own desktop and cleaning the team's central server.
Know the command, but treat it like a loaded gun.
Excellent distinction. Okay, we've covered the connection, the structure, the safety check, and the danger zone.
Oh, yeah.
Let's bring this all together for the listener. What's the final wisdom they need to carry forward?
Instead of just reciting commands, let's summarize the 4 core principles of a successful push strategy.
Okay, principle 1.
I'd call it the tracking contract. Remember that git push you is your one-time commitment. It creates the tracking relationship that enables simple, future git push commands.
Think of it as automation for lazy developers who are actually diligent about setup.
I like that. Principle 2, origin as authority. Always respect origin as the source of truth, both for collaboration and for ensuring your critical work has a secure backup.
When you push, you are submitting your work to this authority.
Precisely. Principle 3, the superset discipline.
If your push is rejected, it means your local history is incomplete. Git is protecting you and your team.
Right. You must stop, pull down the remote changes, merge or rebase them, and only then attempt the push again. That discipline ensures history integrity.
And the last one.
Principle 4, the force boundary. Recognize that git push force is a destructive tool reserved for highly specific private branch cleanup, usually involving a rebase. Never use it on shared branches unless you have explicit documented team consent.
Master these principles, and you've successfully unlocked collaborative professional development. It's the essential bridge between the solitude of your local machine and the reality of working on a complex, moving project with a team.
It connects all those careful local commits and makes them tangible, visible assets for the wider project.
So what does this all mean? The push rejection mechanism, that strict enforcement of the superset rule, it exists specifically because distributed version control systems prioritize history integrity above all else.
Yeah, even above speed or convenience.
So think about this for a moment. If Git didn't enforce the superset rule and simply let the last developer to push overwrite everyone else's work, What would that do to the viability of large, complex, decentralized projects?
Chaos. I mean, if the remote just accepted the last incoming history, regardless of what it contained, we wouldn't have version control. We'd just have the world's most frustrating file synchronization tool.
Yeah.
The complexity of that potential chaos is precisely why that pull, merge, then push sequence is the hallmark of professional development.
Thanks for joining us for this deep dive into pushing code safely and successfully. We'll see you next time as we continue our exploration of professional Git workflows.